Good morning. My name is David Abisher. Our team is part of the U.S. Army Communications Electronics Command Training Support Division. Our presentation today will be about soldiers. Soldiers are deeply rooted in our team's history. They are our coworkers, colleagues, our friends, our parents, and our children. They are why we are here today. The Training Support Division's Virtual Logistics Assistance Representative, VLAR, is a tool designed and developed and tested with a singular purpose: to sit in a soldier's hands and make him or her better. It was built to teach. It was built to learn. About 6 years ago, this team decided on an operations research approach to codifying expert knowledge on Army equipment and applying that knowledge to help reduce uncertainty in combat situations. What you see and hear today will be a story that infuses a classic knowledge management spiral with operations research techniques, from socializing advanced technical concepts and drawing out tacit knowledge, to integrating expert knowledge, to creating an intuitive and instructive interface, and finally, to making VLAR a part of a soldier's everyday life. This story will not focus on profit. It will focus on soldier capital. It will not focus on return on investment. It will focus on soldiers returning safely from combat missions. It will not focus on cost savings. It will focus on life saving. Our team is fortunate to have the full support of our CECOM command personnel. They have nurtured this project since its inception by providing opportunities to demonstrate VLAR capability and by pushing us to find its full potential. It's my honor now to introduce the U.S. Army CECOM Chief of Staff, Colonel Charles E. Harris III.
Good afternoon. I'm Colonel Chuck Harris, Chief of Staff of the U.S. Army Communications Electronics Command. Thank you for the opportunity to address the 2016 Edelman Prize Committee. I am pleased to introduce the CECOM Equipment Diagnostic Analysis Tool, Virtual Logistics Assistance Representative, or the CDAT VLAR, a game-changing capability for our soldiers and our CECOM enterprise. This technology uses advanced operation research techniques to harness the power of the collective CECOM knowledge base and places it in the hands of our soldiers. This capability comes at a time when it is most needed, as the task of keeping our combat forces ready to meet all global threats becomes more and more complex and increasingly necessary. The Army is challenged to maintain operational availability for its combat weapon systems all over the world in a resource-constrained environment. CECOM equipment in particular is increasingly high-tech and more difficult to maintain than ever before. It is imperative to provide our soldiers with the tools necessary to sustain the equipment at the point and time of need and reduce the dependence on on-site support. The solution lies in the ability of the C4ISR community to extend its collective knowledge base through an interface that is both diagnostic and instructive. Through an innovative knowledge engineering process, CECOM has developed an artificial intelligence capability that effectively models equipment problems and provides fast and accurate solutions to those problems. Our soldiers are trained to never give up and to always find that one more thing they can do to survive in combat and complete their mission. What you will see this evening is that VLAR is one of those one more things. Soldiers depend on their equipment with their lives. VLAR helps ensure their equipment is mission capable when it is needed most. Thank you very much for allowing us the opportunity to present this capability to the committee.
There's always one more thing you can do to influence any situation in your favor. And after that, one more thing, and after that. The more you do, the more opportunities arise. Lieutenant General Hal Moore wrote that in his book, Battlefield Leadership, as one of his 4 principles for conduct in battle. And he famously said that directly to the men he was training to go fight in the Luang Valley in the first major conflict of the Vietnam War. As Colonel Harris suggested, CDAT VLAR is one of those one more things. But to understand the application of VLAR, it is first necessary to frame the problem in time and space. The documentary film Restrepo has been called the most accurate war film ever made. The film details a small Army unit's 15-month deployment to a small combat outpost in the Korengal Valley, Afghanistan. The film is named after Private First Class Juan Restrepo, who was killed in action during the first month of the unit's tour. What we will show you now is a typical combat outpost scenario with a couple of the CECOM systems that these soldiers use on a daily basis. This is a 60 kW tactical quiet generator. The generator is the outpost's only source of electrical power for combat and life support systems. The generator is the lifeblood of the camp. This is the unit's satellite communication system. This is the unit's only transmission path to the tactical internet, mission command, surveillance, and intelligence systems. The satellite communication status of every unit in Afghanistan is briefed to command every day.
Change came when we put in OP Restrepo. In the middle of the night, we put up a Firebase on top of the place that they had used as their enemy kinetic, point of attack or origin of their attack for the last 15 months.
We walked up the spur with shovels and picks. We worked all through the night just to make a small semicircle to chill in. We slept for maybe a couple hours each, started doing it again. That day we got in 5-7 firefights. We'd dig, they'd shoot at us, they'd see us digging, building this new place, they'd shoot. We'd shoot back. Once it lulled down, we started digging again.
When the boys built that base, Taliban or the AAF forces in the valley, they were completely in shock. It was like a middle finger sticking out. And they realized once they could not knock off OP Restrepo, we had the upper hand. They started becoming afraid.
What you're seeing now is observation post Restrepo. Please take a few seconds to absorb this scene. This is where 20 soldiers lived and fought for over a year. How can we help them? The portion of Restrepo you just saw makes the problem before us clear. Our combat soldiers operate complex equipment in locations isolated from their main unit by rugged terrain and enemy threat. Combat outposts are manned by highly trained infantry soldiers, but with little formal training or experience in maintaining equipment. In this environment, the consequences of equipment failure can be dire. If these systems fail in combat, soldiers have to depend on on-site support visits. It's inherently difficult to get personnel there to assist, and that in itself is risky. It is equally difficult to get repair parts to remote locations, and misdiagnoses may set up a chain of events where equipment stays inoperative for days or even weeks. It was not long after seeing that film that our team was asked to start researching how CECOM was approaching combat outpost logistics in Afghanistan. Afghanistan was different. Different tactics, different terrain. To our team, the existing strategy for supporting these troops was untenable. When VLAR development began, one thing was clear. This is where our soldiers live. So from a design perspective, we must live there as well. What this means is that every piece of diagnostic advice we give a soldier must assume the most austere conditions, extremes of weather, high threat, limited experience, limited tools, and 10 minutes of battery life left in their electronic device. The nature of the conflict meant that there were a lot of commercial technologies in use, along with communication systems, surveillance systems, and life support systems. All of these systems are critical, all of them complex, and all of them need electrical power. VLAR is designed with the combat scenario in mind, and its underlying assumption is that given expert advice, a soldier using VLAR may be able to do that one thing that gets his piece of equipment back up to keep his fellow soldiers alive. The VLAR team developed 2 research questions to guide development from this assumption and from its design imperative. How do we take the collective knowledge of CCOM system operations and maintenance and codify that in a diagnostic and training tool usable by anyone, anywhere? 2, how do we extend the CCOM knowledge base to remote locations and to remote operators? And how do we make these remote operators more self-sufficient? The combat outpost logistics issue compels us to reason counterfactually and answer those research questions in those terms. What would the alternative have been had the equipment supporting those troops not broken down at the point in time of need? Even more to the point, what would have happened had they been able to repair it? How can we best intervene? CCOM's primary mission is to support soldiers. That mission is conducted by the combined efforts of men and women in a number of different professions, all sharing the same goal. Our profession, as members of Training Support Division, is training soldiers to operate and maintain complex equipment in combat. In this pursuit, we have always been constrained by our own numbers of personnel and by the time we have available to engage with soldiers. And these research questions have challenged us for years. Only the combat locations and the equipment complexity have changed. Operations research has breathed new life into our profession, a profession that was losing its edge in keeping up with the demands of technology in global combat scenarios. It has given us the tools to battle new tactics with new technologies and to keep pace with the growing complexity of combat system. Operations research has fundamentally changed the way we approach diagnostics and the way we approach training and transfer of knowledge. What you will see and hear about now is a set of innovative operations research techniques that comprise our VLAR development process, a process that makes artificial intelligence seem less artificial, and a process that ultimately makes a tool that, when placed in a soldier's hands, bridges the gap between our knowledge base and our soldiers. What you will see and hear about today is a story of a still evolving process of engineering knowledge that improves soldiers' lives. We feed this process theory. We feed it knowledge gained from careers in the field working with soldiers. We feed it knowledge from hundreds of cumulative years of deployment in combat situations. The strength of VLAR is its ability to reason like an expert. But how do we make VLAR look like a Robert or a Rod or a Chris and blend the theoretical, the experiential, the heuristic to enable a machine to make a diagnostic choice that only a veteran of years of experience could make? Operations research applies the formalism to all this and renders a product that teaches, does, and learns. To do this, we must first describe the basics of the causal Bayesian network and the process whereby the finest details of expertise are expressed within a conditional probability table. Causal Bayesian networks combine the qualitative in a directed acyclic graph and the quantitative in a conditional probability table to fully represent the probabilistic relationships between variables. Regardless of the size or type of diagnostic problem, building a directed acyclic graph is the first output of the define, structure, elicit, verify, DCEV process we will show in detail, and the first step in building a causal Bayesian network. The directed acyclic graph is non-parametric, a wholly qualitative model of the problem and the relationship between its variables. The building blocks of the graph are nodes representing variables and arcs representing temporal cause and effect relationships. The presence of an arc is an assumption of causal effect, and the absence of an arc is an even stronger assumption of no causal effect. The 3 node and arc structures are used to put the knowledge of experts into a causal model using the process we will describe. To go from this qualitative model to a causal Bayesian network is where the magic happens, where the artificial becomes less artificial. What goes in the table requires omnidirectional and multidimensional thinking and consideration of all the points on the hypercube. It is a daunting task considering the sheer number of ways machinery can fail and the physical principles of electrical theory, wave theory, radio frequency, and thermodynamics that are all in play. The conditional probability table is our mechanism for representing the most complex relationships between variables. Theory guides the expert and provides explanatory power when combined with experience and a causal model. But the diagnostic path following the theoretical principles infused with expert knowledge may seem counterintuitive to someone that is inexperienced. VLAR codifies all of that, clarifies confusing signals, and educates. From all this, you will see how VLAR has enabled a shift in the Army's sustainment paradigm. It is my pleasure now to introduce Dr. Joe Tapman and the define, structure, elicit, verify process we use for capturing tacit knowledge from experts.
Thank you, Dave, and good morning. The elicitation problem is to bridge the gap from knowledge in the heads of experts to knowledge in a usable, accessible model. The solution we used is the define, structure, elicit, verify, that is DCEV modeling process. The most important feature is that the mathematical precision of the target causal Bayesian network enforces discipline and structure on the human process. CCOM has little or no hard data on field usage and troubleshooting events, only paperwork that has no traceability back to actual events and only limited context. None of this could be used for building VLAR. However, CCOM does have a very robust cadre of experts stationed worldwide with years of experience working with soldiers and equipment in combat environments. This knowledge had to be captured in a model that could be used as the brains of the VLAR software. The model is causal Bayesian networks. IDI has developed a process for building causal Bayesian networks from groups of experts. It is called the Define, Structure, Elicit, Verify, or DCEV process. It is a documented process that has evolved over many years of experience of building causal Bayesian networks from expert panels. A short description of the steps of DCEV follows. Let's build the DCEV process from the experts on the left of the slide to the models on the right. Before the experts can start building the model, the problem must be framed. What is the appropriate level of abstraction? Do we model how the system is supposed to work or how it fails? Is there a single failure mode and a single causal Bayesian network or multiple? The answers to these questions can be different for each application. We must prepare the experts. They must be oriented to what will be required of them, how their answers will be used, and motivated by the importance of their contribution. Experts usually need some practice answering elicitation questions to feel more comfortable providing their judgments as probabilities. In addition, the knowledge engineering team must become familiar with the jargon of the application area and become acquainted with the way the target system works. The VLAR knowledge engineering team, in preparing themselves for meeting with the experts, followed a robust process for getting smart on the target system. This internalization included study and analysis of tech manuals and formal training on the target system. This preparation had the side benefit of providing credibility for the team when they went in front of the experts. Human dynamics like this are important in working with experts to build causal Bayesian networks. Before the DCEV cycle begins for a causal Bayesian network, the knowledge engineering team needs to brainstorm with the experts the nodes that will provide the information for the node representing the diagnosis. The knowledge engineering team modified this process to instead brainstorm a list of cause-effect relationships. These together establish a linkage from causes to negative system effects, key for building causal Bayesian networks. The DCEV cycle is iterative. Each time through, the knowledge engineering team leads the experts through incrementally selecting and defining in detail one or two causal relationships to add to the net from the brainstormed set. Highest priority first. These nodes are wired into the existing causal structure, refining the directed acyclic graph. This is the structuring step. Their conditional probability tables are then elicited, and the resulting subnet is immediately verified while the experts are present and their provided knowledge still fresh. The addition of each small set, therefore, each small set of nodes results in a limited but working and verified causal Bayesian network of the highest priority effects. The process is finished by validating the model. The VLAR team uses a panel of system experts that have not been involved in the development process to confirm the elicited models. The final validation step involves live testing with untrained soldiers on failed equipment returning from the field. Upon validation, the causal Bayesian network is transferred to the system development process. I'm now happy to introduce Andrew Vatterott, who will describe this process.
Thank you, Joe. Good morning. My name is Andrew Vatterott, and I am the Knowledge Engineer Team Lead for the VLAR project. Today, I will be sharing our approach to developing VLAR, along with a sample of the user interface itself. As Dave illustrated earlier, VLAR had its genesis in helping soldiers in remote combat environments. With that in mind, the mission statement of the Knowledge Engineering team is clear. Build a soldier-centric diagnostic tool that is effective, educational, and intuitive. The Knowledge Engineering team must address two main questions. One, how do we capture expert knowledge? And the second is, how do we make that knowledge useful to the soldiers? To better describe how we go about addressing these questions, let's look at a practical causal Bayesian network. This is a small causal BayesNet segment and conditional probability table from an existing generator VLAR module. The input-output module, or I/O, is a component on the generator that allows the onboard computer interface module to communicate with the rest of the symptom. The heartbeat LED and speed control LED are both system indicators that represent different I/O functions. So in this example, expert knowledge tells us that the I/O has more than one failure mode and that the heartbeat LED is not a reliable indicator for I/O failure relative to the speed control LED. This is important for diagnostic purposes, as it guides soldiers away from making a diagnosis solely based on the state of the heartbeat LED, as had been the case before. This new information is not available in any technical documentation and could only be determined through direct elicitation with experts. And it is the DCEV process that enabled us to do so. This completely changed the diagnostic approach, immediately reducing misdiagnosis of systems. This here is a causal BayesNet in its entirety, verified by experts, that is currently integrated into VLAR. The knowledge is there, but it's not yet useful to an end user. This is our tool called a system network, which maps the troubleshooting processes elicited from system experts. It serves to connect and guide the users through the causal BayesNet. Once we have a confirmed process, we write out and photograph all inspections and testing procedures that are then presented to the user. For purposes of this demonstration, I built a simplified SystemNet, or process map, and probability model for the symptom engine runs erratic at idle to illustrate how the soldiers interact with causal BayesNets in real time. Before we continue, take a moment to look at the model. Pay particular attention to the green node in the center and the light blue node directly above it. And now I'd like to show a scenario for troubleshooting this symptom in VLAR. This is the generator home screen where users will select the most appropriate symptom. In this example, the user selects engine runs erratic. After they select the symptom, this is the first screen that they'll see. This is a standard slide format for basic inspections or questions about the system. The top line there is either a question or directive statement. There is a user-entered radio button which responds to that. The main body of text in green contains necessary descriptions and or instructions for performing procedures. And to the left, there are relevant pictures to act as visual aids. Now, how does this tie back to the sample causal BaseNet and SystemNet? The radio buttons that the user sees are actually the different states of a node in the causal BaseNet. And as mentioned earlier, the process is driven by the system network. So for every slide that the user sees, there is both a causal BaseNet node and a SystemNet node behind it. When operators interact with VLAR, they are actually interacting directly with the probability model and following an expert-defined path. In our example, the user entered evidence into that green central symptom node. Notice the effect that entering evidence has on probabilities throughout the network. As the operator continues to navigate through VLAR, the model continues to update in real time behind the scenes. Notice how the probabilities have changed yet again. VLAR will continue to guide the user based on evidence that they enter, but not always in a linear fashion. VLAR has the capability to compare likelihoods of multiple events and make calculated diagnostic decisions on the best course of action for the soldier to take. Now that we have gone through all of the appropriate slides, let's look at the sample causal BaseNet once again. Look at the outlined light blue nodes. Each piece of evidence that we entered contributed to the resulting probabilities contained in those nodes. And here is the end result of this scenario. Based on the evidence that was entered, the user is presented with a list of potential failures in the order of most likely to least likely. Without even realizing it, soldiers are using a powerful analytical tool that contains the collective knowledge and experience of system experts right at their fingertips. VLAR enables and trains the soldiers to troubleshoot like experts. With that, I'd like to introduce Michael Grimes, VLAR's project manager.
Thank you, Andrew. Good morning. My name is Michael Grimes. I'm the project manager for the VLAR. VLAR has demonstrated actual and potential impacts, both quantitative and qualitative, and the Army's primary currency is its readiness. Simply put, the Army units are measured by how able they are to put forces in action at a moment's notice. Without readiness, missions fail. During testing, we have put VLAR in the hands of real soldiers, and it has demonstrated every time a profound effect on the soldiers' performance in troubleshooting multifaceted problems. We will see similar results with every user of VLAR. As you can see in this diagram, Corporal LaFrieda started this test with no prior experience with tactical generators. By week 3 of the test, his average time to diagnose a complex electromechanical subsystem was just 20 minutes with 100% accuracy. Corporal LaFrieda is now leaving the service in the next few months, and after a distinguished career in the Army, he has secured a position with a leading power generation maintenance contractor based solely on his experience troubleshooting a 60 kilowatt generator with the VLAR. Sergeant Travis Hoyle stated, "Not only are soldiers becoming more proficient, but in some cases they are exceeding expectations in their knowledge and applying it to other aspects of the mission after using VLAR." Because VLAR has proven that it helps soldiers, it also has many benefits to the CECOM enterprise in how it can leverage accurate field data from VLAR to improve their ability to make supply chain and buy or repair decisions. Gary Solomon, Associate Director of CECOM, will explain VLAR's value to the enterprise.
What we're seeing with VLAR as we deploy it on a number of systems, the combination of cost avoidance, the ability to troubleshoot faster, the ability to collect data, and the ability to have it impact readiness for the soldier is in every way, shape, and form a game changer, a paradigm shift Can't emphasize enough that this is not simply a incremental improvement in our capability. It's a tremendous impact to us.
As Gary Solomon discussed, VLAR is crucial and may mean the difference between success and failure of a mission. Without VLAR, soldiers are required to request external support, and this support requires vehicle convoy or helicopter movements that can take days or weeks to arrive. This puts both soldiers and civilians at risk. With the VLAR, these movements can be significantly reduced or removed completely, saving money, time, and most importantly, preventing injury or death. The VLAR system was first fielded to Afghanistan for the high antennas for radio communication, HARC system, and for tactical generators, both systems that were prone to failures requiring on-site support. Prior to the VLAR fielding, the HARC required over 25 full-time support personnel, and VLAR dramatically improved operational availability of the HARC through a completely new approach to diagnosing the optical circuit. VLAR enabled a shift from a personal intensive support strategy to a strategic help desk support strategy. And VLAR removed the need for on-site visits and reduced the number of personnel required in Afghanistan from 25 to 1. HARC field service technicians cost reductions of $20 million total since implementation of VLAR. We are anticipating $10 million per year into the future. In addition to cost reductions, we were able to calculate movement reductions for the systems with VLAR. We determined causality or casualty avoidance as a product of repair movements avoided per repair by the number of repairs per year by the number of casualties per that movement. Historical data starting in 2013 indicates that each of 525 HARC system repairs and 60,000 generator system repairs requiring movements have been avoided. These repairs would have required 3 air movements and 3 ground movements on average each. The Army Environmental Policy Institute's estimated 1 soldier or civilian casualty killed or wounded in every 41 ground logistics convoys. The Joint Aircraft Survivability Program Office estimates 1 soldier or civilian fatality in every 8,300 helicopter flights. We have proven that because of these reductions, we have avoided 4,500 potentially wounded or killed soldiers. Linda Bilmes of the Harvard Kennedy School has written a paper estimating that each of 900,000 veterans with disabilities will cost the nation $1.1 million over the next 5 or 6 decades. We consider it much more likely that the 50,000 veterans who have been wounded in action would account for a much higher cost on average than the broader set of veterans with those disabilities. So we conservatively use a factor of 2 to estimate the proportional increase. Taken together, we estimate that the reduction in casualties associated with VLAR will save the government at least $9 billion in current or future costs. The HARC and generator fielding has proven that we are improving system operational availability by using an OR approach. An analysis by CCOM quantified that VLAR is a critical component of CCOM's fleet management strategy, and VLAR was used to diagnose a population of 100 generators returning from Afghanistan that were designated for overhaul. The VLAR test identified that 78 of the 100 did not need that overhaul. These data show a 30% increase in the operational availability. Additional analysis has demonstrated significant cost avoidance. And there are currently 40,000 generators fleet-wide that go in for overhaul per year. VLAR projects a cost avoidance of $315 million on 11,000 generators that would not be sent to depot because they were not misdiagnosed. The final recommendation from this test was that CDAT VLAR be now used for all screening generators prior to overhaul. Now, we apply the VLAR methodology to different types of equipment domains: electrical, electronic, optical, radio frequency, and even electromechanical. We've also demonstrated that our cost model stays stable while the benefits grow for the number of the systems. Single investment in VLAR for generators reap benefits for an entire fleet of over 70,000 generators. This makes VLAR scalable, portable, and cost-effective for any military or commercial application. Currently, CCOM has mandated that VLAR processes and tools be developed for 60% of their most complex CCOM-managed combat systems. This is approximately 60 systems. To support this pillar, CECOM has budgeted $10 million per year to VLAR development. Dave Abisher will now talk about the impact at Army level.
The mission of the DoD Maintenance Symposium is to create an environment that enables attendees to share relevant information, identify critical issues, discuss key topics, and increase their awareness of Department of Defense maintenance initiatives. At this event, attendees have the unique opportunity to influence the future of the maintenance community. VLAR was selected as a presenter at the 2016 event as a key component of CECOM's Condition-Based Maintenance Plus program. The Army's G4 staff, responsible for setting Army maintenance policy and strategy, recognizes the impact of VLAR on current and future maintenance operations. We live in a complex world with complex threats, said Major General John F. Wharton, Commanding General of the U.S. Army Research Development and Engineering Command. Wharton, the host of the 2016 Army Innovation Summit held at Aberdeen, Maryland, welcomed technology leaders from across the Army. Our goal is to foster innovation, he said. The Army operating concept defines innovation as the result of critical and creative thinking and the conversion of new ideas into valued outcomes. The following video places VLAR in the middle of the Army's operating concept. VLAR is demonstrating impact from the field level through the command level all the way to the Department of the Army level. CDAT VLAR was selected as CECOM's showcase for the 2016 Innovation Summit. The summit is a series of meetings between senior Army leaders that determines what innovations will be integrated as part of the Army fleet. The keynote speaker for this year's summit was General Dennis Vai, Commanding General of the U.S. Army Materiel Command. General Vai first saw VLAR in Afghanistan in 2010 as a fledgling project aimed at improving CECOM logistics processes in theater. He was pleased to see that VLAR had progressed.
And where all do you have it now, actually, in Afghanistan?
We have it in Afghanistan, all the different HARC sites.
Okay.
All the PTID sites in Afghanistan.
Okay.
And then all the TQGs, everybody that's using a TQG over there.
Outstanding. Well, good. Well, great to see all the great progress so far, and keep up the great work, okay?
Yes,
The Army supports its combat forces by a number of sustainment processes, broadly categorized under supply and maintenance operations. All those operations share a common requirement: to know what is needed and where. The foundation of maintenance operations is accurate diagnosis of the problem. Operations research has changed the way the Army does sustainment. Operations research infuses the VLAR product with a rich set of capabilities that advance the art and science of diagnosis. And it does so at the very edge of tactical operations where soldiers depend on their equipment with their lives. VLAR is the first and only Army effort to incorporate operations research in diagnostic processes and empower soldiers with a new and robust capability. Thank you.